Hi, everyone. So let's say that we're drawing the three cards from the deck without replacement, meaning that the drawn cards are never returned back to the deck. What then is the probability that we're going to get this sequence? An ace first, then a king second, then a king third. Remember that when we drew or sampled with replacement, we got this probability, which was pretty low. Now, if we sample without replacement, if we draw the cards without replacement and we don't return them immediately, do you think this probability for without replacement is going to be higher or lower than this probability with replacement? Is this sequence going to be more likely or less likely now compared to before? I'll give you 30 seconds to think about it. Okay, now before we get to the calculations, we need to introduce an important idea, the idea of conditional probability, which we're going to need if we're talking about dependent events. This is the probability of B given A. Important notation. This is the conditional probability, think updated probability, that B occurs given that A occurs. Now, this idea of updating probabilities is a popular idea, and it's a practical idea among Bayesian statisticians, although it is controversial. There are some purists who don't like the idea of updating probabilities, but I think this is very practical. I was trained as a Bayesian. We're going to talk about medical diagnoses later on. So what is the general multiplication rule for the probabilities of and? So the probability of A and B, that's the probability of A times the probability of B given A. That is, given that A has occurred or is guaranteed to occur. So here's an example. Let's say that you're looking for a date and you go on, I don't know, Match.com or Tinder or something. And let's say that you're looking for someone who is rich and good looking. You're kind of shallow. So then you might ask the dating site, okay, so find me the rich people. And then what do? Are you going to do a brand new search for the good looking people? No, you're going to filter among the rich people. Who are the good looking people? So the probability that a random person is rich and good looking, according to your criteria, is the probability that the person is rich times the probability that the person is good looking, given that the person is rich. You're conditioning on the person being rich. It's not a brand new search. You're filtering. It's like a filter. Likewise, the probability of A and B and C is like a military scenario. It's the probability of A happening times the probability of B happening, given that A has happened, times the probability of C happening, given that A and B have happened. Again, it doesn't have to be a time sequence, but the idea is that the events that you're conditioning on are assumed to have happened or are guaranteed to happen. So as you build up this calculation for the probability, you're assuming that the previous events have already happened. That's the idea. Now, this is a general multiplication rule. What if A and B are independent? For example, consider the issue of rank and suit. Like, for example, what's the probability that you get the 3 of hearts if you draw a random card from a standard deck? Well, it's the probability of getting a 3 times the probability of getting a heart, given that you've gotten a 3. But now, wait a minute. Let's say that you draw a card, and I look at it, and I tell you that you drew a 3. Well, what then is the probability that you have a heart? Well, I know you have a heart, but I mean a heart on your card. Well, wait a minute. Does the fact that you got a 3, assuming I'm honest, is the fact that you got a 3 relevant? Well, no, it doesn't matter at all, because what's the probability that you have a heart? Whether it's a 3 or not, that probability is 1/4. It doesn't matter what rank it is. So if A and B are independent, like the issues of rank and suit, then the occurrence of A does not change the updated probability of B. The probability of a heart stays 1/4. So that means that the probability of B given A is just the probability of B. The probability of this conditional probability is just the probability of getting a heart. So then you're back to the multiplication rule for independent events. The probability of A and B is just P of A times P of B. This conditional probability degenerates to the basic probability. So this is a general multiplication rule that applies to both independent events and dependent events. All right, now on to this example. What's the probability that you get the sequence ace, king, king? We need to build up this scenario. So the probability you get an ace first and a king second and a king third, because we're sampling or drawing without replacement, these are dependent trials. The probabilities for these kings over here will depend on the previous probability of getting an A. In fact, the probability of the third king will depend on these previous draws. So the probabilities for subsequent draws will depend on what happened on previous draws. All right, so this probability is equal to the probability of getting an ace first times the probability of getting a king second, given that you got an ace first. We're building up the scenario, times the probability you get a king third, given that you got an ace first and a king second. We're assuming that you're succeeding along the way. Let's say you win if you get this sequence. In order to win, you have to assume that you've been building up the win on previous draws. An ace first, then a king second, and then a king. All right, now what's the probability of getting an ace first? Well, it's the same old, same old. I mean, we have 13 equally likely ranks. The probability of getting an ace first is still 1/13. But for the purposes of this problem, let's say that it's 4 out of 52, which is also correct, 4/52, because there are 4 aces out of the 52 cards. Now, so that's for this probability. Now, assuming that, conditioned on you getting an ace first, what's the probability that your next card is a king? Now, if you get an ace first, are you a bit more likely to get a king next or a bit less likely? Actually, you're a bit more likely, because I'm assuming that the first card you drew was not a king. We're sampling without replacement, and we have a finite number of cards. So if you drew a non-king first, you're a bit more likely that the next card will be a king. Now, what is this conditional probability? I'll do this in blue. Well, we start off with 52 cards. If we're assuming you drew an ace first, what's the probability that you get a king next? Well, how many cards are there left in the deck? 51. And how many kings are still left in the deck? There's still 4. We're assuming you drew an ace first, so I'm assuming that all 4 of these kings are still in play. So 4/51. That's the conditional probability. And then assuming that you got an ace first and a king second, I'll do this in purple. What's the probability you get a king next? Well, how many cards are left? 50. We've already drawn 2 cards. But wait a minute. We've already drawn a king. We're assuming we've already drawn a king. So how many cards are left? How many kings are left out of the 50 cards left in the deck? Only 3. Let's say we first got the king of hearts, right, as our second card. Let's say we got the king of hearts as the second card. Then there are only 3 possible cards, 3 possible kings remaining that you can pull. These over here. So 3/50. 4 over 52 times 4 over 51 times 3 over 50. It's like countdowns. As you draw out cards, you're decreasing the denominator by 1. And then depending on what the previous cards are, how many of the desired card, the desired rank, is left. And the answer you'll see is about 0.000362. More interestingly, it's a little bit less than what we got from the first example when we sampled or drew with replacement. This was 0.000455, give or take. Now, why was this lower? Because at first you might be saying, well, wait a minute. If I draw a king, if I draw an ace first, I'm actually a little bit more likely to draw a king. That's true. Notice 4 over 51 is a bit higher than 4 over 52. If you lower the denominator, you're raising the fraction. But wait a minute. Look at this third probability. We're assuming you've drawn a king on the second card. Now, if you've taken out one of the 4 kings, you're a lot less likely that you're going to get another king. So even though you get a slight bump up from here to here, there's a big drop from here to here when you drop the numerator from 4 to 3. That's a big drop there. So it's not as likely you're going to get the third card to be a king if your second card was also a king. That's why this is lower, substantially so. What kind of order triple would be least likely when it comes to ranks? What kind of order triple would be least likely? I would say something like, how about ace, 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 or queen, 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 or 10, 10, 10. 3 of a kind. If you're drawing 3 cards without replacement, then it's very unlikely that it's a lot less likely you're going to get all 3 the same, because then you're going to get big drops in these conditionals. With replacement, it didn't matter. It was 1/13 times 1/13 times 1/13. But without replacement, hey, every time you draw out a queen, you're a lot less likely the next card will be a queen, and so forth. Okay, next up, what's the application for poles?